So today we'll be doing something which is known as dynamic programming, and I think you can see that here. If you're wondering how I did that, uh, well, a magician never reveals their secrets. So uh, maybe I'll tell you all later on. But basically, today we'll be in the world of algorithms and we'll be seeing how different algorithms work out. So, first of all, can someone help me out with what exactly is an algorithm? Anyone here? Yeah, sure, go ahead, speak.
Yeah, set
It
of
is a
rules
set of
that compute
instructions.
develops.
Either of you can go ahead. Set of instructions, both of you were saying. Yes, that's correct. Set of instructions, which is usually given to perform a certain task and do a certain amount of calculations in a certain way to get a final result. That's sort of what an algorithm is. And in particular, in this class, we will be looking at algorithms which are called optimization algorithms. As the name suggests, optimization algorithms deal with trying to minimize something.
Wait, are you
Right?
sharing the screen or not?
I'm not sharing. If you're looking for where I'm writing, it's over here. Maybe I should write a little bigger. Is that,
It's on his camera, so like pin his
So
video.
his
yeah.
screen is camera, thanks.
So what we'll be dealing with today are optimization algorithms. And these are very nice because they usually deal with minimizing a certain thing, or say maximizing a certain thing, or trying to find the shortest path, or trying to find the best way to do a certain thing, or find the worst way. I don't know why you would find the worst way, but maybe, who knows. So the idea of these optimization algorithms is they can help you make choices which may not be very obvious, because certain times you have a lot of choice and it's not immediately clear what choice is most beneficial for you. But these optimization algorithms can tell you what is the best thing to do and can save you from that choice and help you make the right thing. So dynamic programming essentially is an optimization algorithm which deals with helping you figure out how to minimize or maximize stuff. We won't be getting into that just yet though. I would like to speak a bit about time complexity. Um, Basically, we define the notion of an efficient algorithm. Like, one second. There are a lot of times when it is possible to brute force through all possible options. It's like, let's say you had n events and your optimization algorithm basically needs to tell you ki, out of these n, should I take the first three or should I take these four? What set of events should I take to perform like in certain criteria, and I want to maximize some value. And what you could do is just try everything, try every possibility. There are 2 to the n possibilities because each event can be picked or cannot be picked. So there are 2 to the n possibilities, and each possibility you figure out what is the value and how it works out, and then you find the maximum across each of these possibilities. The problem with 2 to the n though is it's exponential, right? So it rises really fast. So for example, if you have, let's say, 100 events, then 2 to the 100, can someone approximate 2 to the 100? It's like, okay, I'll just do it. It's basically 1024 to the 10. So if I take that as 10 to the 3 to the 10, or this is 10 to the 30. Um, 10, so a computer can usually do around 10 to the 8 operations in a second, and even if you take each check as an operation, then this is still uh, greater than 10 to the 22 seconds for a computer to do this. And just to make it clear, 10 to 22 is greater than the time the universe has existed for. So that's definitely beyond us. I think if I'm not wrong, the universe has existed for some 10 to the 20
and
seconds.
second is not the answer.
Sorry?
I think 10 to the 22 is not that large time.
I mean, no, see, universe existed. I was talking about Big Bang. Big Bang happened. Let's see, when did the Big Bang happen? Big Bang time 13.8 billion years. So 13.8 into 10 to the 9, 10 to the 9, right? Yeah,
Yeah,
into
billion means
10 into 365 into 86,400. I'll just put this up. This, right? How many
Yes,
zeros are
yes,
here?
yes. It is smaller than 10 to the 24.
It's much smaller.
Yeah.
So, I mean, this is like beyond our thing by far. This, even if there were like less than 100, I could have taken some 50 events or something. Then also this would be too large. So the thing
Maybe
is,
we can sort them out.
sort them out in the sense.
Like sorting using sort.
Yeah, so yeah, I've
Hey,
not got into what algorithm we're using. It's just I'm trying to show that if you try out every possibility, usually it takes exponential time, which is not good at all. What you want instead of this 2 to the n is you want n to the 2 or something. You want n is also okay, n cube is also
So
okay.
you want a polynomial.
Exactly.
Sense.
You don't want exponential time, you want polynomial time. And this is what is usually called an efficient algorithm, which can, in polynomial time, here it's a polynomial in your input. So like if you had n events, it should be an polynomial in that n. The basic idea is that. And if
I
you can
think
get,
it becomes then more efficient to sort. Like we get a range of efficiency for some values of n, and then we try to sort them out.
no, I did not actually mention the problem. Like there were 100 events and you had to do certain, you had to maximize certain thing about it. We have not actually got into a problem. So it may not, sorting may not help, sorting might help, who knows. But
Okay.
like I'm just trying to give an example, a little abstract example. Uh, but we'll get into these real kind of problems, and their sorting is, yeah, a very useful thing. Except sorting itself is an algorithm which is interesting to see, because you need to be careful. Your
We can
thing is,
neglect the phi case, phi empty wala.
yeah, sure, 2 to the n minus 1, but still it's
Yeah.
10 to the 22 minus 1 ho gaya. Not even minus 1 because it was 10 to the 30. But even if it was minus 1, this is,
Okay, can we short other one cases also?
uh, no, I was, oh, 2 to the n or n square, you're saying? This n square? I didn't exactly.
Clearly, we should use polynomial because
Yeah,
that rises very fast.
because 2 to the 100, if this we got as 10 to the 30, and this would be 100 square, this is 10 to the 4. This is obviously much better. In fact, even n to the 15, 14 is better than this. So in general, polynomial time is something that you would really like. And when a question cannot be solved in polynomial time, it's not nice. It's called a non-polynomial time problem. But anyway, so this was a basic idea on time complexity, that usually when we are looking for algorithms, we are looking for efficient algorithms. We're not just looking for any algorithm. Okay, enough of this efficient algorithm business. Let's get into what is dynamic programming. Essentially, it's a technique that is used a lot in computer science. It's used in competitive programming. If you've been there in INOI or IOI type questions, and you'll see it like everywhere you go in competitive programming. But why are we learning this in the math world? The thing is that personally, at least, I believe that even though it is a computer science technique, it's at its heart really just combinatorics. It's really just mathematics. And even though you will never, hardly ever see a dynamic programming question in math Olympiads, it's still something that's probably worth learning. And like in future, if you ever go into computer science, dynamic programming is like going to be obviously really useful for you. And even if you don't, it's just a very fun and interesting thing to learn. So I think it's worth learning. But oh, by the way, I have this interesting story looked up on the origin of dynamic programming. So usually origins are pretty boring, and I wouldn't like want to bore anyone, but this was kind of funny. So it's like dynamic programming was invented by a guy named Richard Bellman. So Bellman explained that he invented the name dynamic programming to hide the fact that he was doing mathematical research. He was working at this place called RAND under a secretary who had a pathological fear and hatred for the term research. Okay. So he settled on the name dynamic programming because it would be difficult to give like a bad meaning to it. Like nobody would object to the name dynamic programming. Basically, this name sounded cool. So why is it called dynamic programming? Name sounded cool. Great. So essentially, what is dynamic programming? We've spoken so much about it, but we have not really seen what it is. It's the idea of breaking down a certain problem into these smaller sections and then joining all of them up together to form like a single kind of thing. So it's basically like recursion, but in the sense, like if you've heard of recursion, then it'll feel like it's the same thing, but it's actually an improvement to recursion. It's you can call dynamic programming recursion plus memoization. We'll see what each of these things really mean. Just to put it in, these are the two parts of dynamic programming that we'll be looking into. So the simplest example of recursion which I can think of is the Fibonacci. I think everyone here would have seen the Fibonacci. Some people like to say F0 is 1 and F1 is also 1, but I don't know. So the basic idea here is that you're defining a aage wala value on the basis of the previous values. So you're using the idea of recursion. Recursion is basically where you instead, so basically in algorithms, what you will usually have is you'll have like a function, like let's say here you'll have the Fibo function, and this Fibo function takes an input. Your input is a value n, which is the number of Fibo, the number whatever Fibo which you want, the nth Fibo, let's say you want, like you want the nth Fibonacci number. So, and the output that you would want of this function is the nth Fibo number. And in between, there'll be like certain steps which will help you find this nth Fibo. So when you have a recursive solution, what usually happens is it's like induction, if you've done induction, where you have a base case. So if n is equal to 0 or n is equal to 1, then you just know the value. You know that for n is equal to 0, Fibonacci was 0, and if n is equal to 1, it's 1. So you can just tell it manually that these are the values. And if n is greater equal to, now you know that this will be equal to the sum of the previous two. Oh, that's not visible. Sorry. So basically what you want now is that that if n is greater than 2, then you calculate Fibo of n minus 1. I'll come down. You calculate FIBO of n minus 2, you add them up, and then you return this value. This is your nth FIBO. Is it clear to everyone why this should work? People?
Yeah, it's clear.
Okay, good. It's clear. So, but can someone tell me why this is in one word, this algorithm, as according to its time complexity? It's horrible.
We need to calculate very much. Like if we could define a function, a real function, so that it takes some values and gives out the answer. But in here we are counting inductively. We need to take out the n minus 1th value. For that we need to take out the n minus 3rd value, and this cycles goes on.
Yeah. So the idea is that see, you will have to anyway calculate f1, f2 till fn once definitely. The problem comes in because you are doing repeated calculations. It's like you, to calculate fn, you have called fn minus 1 and you called fn minus 2. Exactly. To calculate fn minus 1, you called fn minus 2 and fn minus 3. This you called fn minus 3 and fn minus 4. So if you see here, fn minus
While
3
the
has
graph
come
is formed,
twice. Yeah, sorry.
while the graph is forming, so the time will be exponential for so.
Yeah. So the basic point is that you're repeating all of these values. Okay, this you're not repeating, but all of these values are coming multiple times. If you've already calculated a certain value, why are you wasting your time calculating it all over again? Instead, what you should do is um, over here. Okay, this is coming over my face. Let me do one thing. I'll erase this. Yeah. So what you can do is over here, you also, when you're outputting it at this point, you also say, remember this value. Oh, it's still coming over. Yeah. Remember this value. How will you remember it? Let's say you have like an array, like if you know what arrays are basically list of variables which have indexes from 0 to n minus 1. So basically remember that fn, like you originally, let's say, have an array of f, which is from 0 to n, and you have defined each of these equal to minus 1, right? And every time you do calculate a Fibonacci number, you say that, okay, it's no longer minus 1, now I have calculated it. So now this is the value. I have calculated it, remember it. And while starting the function, you say, if this fn is not equal to minus 1, meaning I had calculated it earlier, then just directly solve it. There is no need to do all of this over again. So this is the idea of memoization. Memoization basically says that if I have calculated a certain value, I need not calculate it all over again. Why should I waste my time doing that when I can just remember it and not forget it? So this is the main idea of dynamic programming, to recurse and memoize. Now it might still be unclear to like how would you apply dynamic programming in a question and what kind of questions you apply it to. So there are these 5 steps. I won't be explaining them just yet. We'll do a problem and we'll see how each of the steps come in. The first step is uh, figuring out sub problems. The second step is to guess. And again, I'll come to why exactly we are doing each of these 5 steps. Just give me a little bit of time. The third step is to build a recurrence. The fourth step is to recurse and memoize. And the fifth step is to solve the original problem. Okay, but we'll come to where exactly we apply each of these 5 steps. For now, let's go on to a nice and sweet problem. The first problem that we'll be doing is around, wait, let me just see what's the name of the problem. I don't actually know. Okay, it's called rod cutting. I don't know, weird name. Oh, by the way, is green visible? Maybe I should not use green. I'll use it blue. Okay, so the question is basically that you have a rod of a certain length. Let's say it has length n. And I don't know, maybe this is a rod of plutonium or something. I'm not very sure what it's a rod of, but it's pretty expensive. So it's like you can sell this rod for a certain amount in the market, and the amount which you can sell it for is different depending on the length of the rod. Let's say if you have a 1 meter rod, then you can sell it for 50,000 rupees. If it's 2 meters, then it need not be linear. It need not be 100K now. Maybe now it is even more valuable, 120K. If it's 5 meters, then it may be less expensive. It'll be like 200K or something. Like there are some values which are given to you that for different rod lengths, there are different prices. And basically what you want is you have a rod of length n, you want to cut this in parts so that you can maximize the total value that you're earning.
Maybe
So it's
cut
like,
this in only the part of.
sorry?
So maybe cut this in only the part of.
Yeah, that's it's not necessary, right? Especially if you have like n is equal to 7. And here you could maybe choose this one and this one, or you could choose 7 of this one. I think 7 of this one just works here. Maybe I should change the values a bit. Oh, sorry. This is 20K, let's say. So it's definitely not very obvious. Like what if you had a 3 meter and 4 meter here? Then you would have to check whether a 3 meter plus 4 meter is better, or a 5 plus 2 is better, or a 5 plus 1 is better, or just 7 ones is better, or 4 plus 2 plus 1 is better. You never know which one is the best thing to do. So you want to build an efficient algorithm which tells you what is the best value you can earn so that you don't lose out on any money. And we'll be using dynamic programming. Would people prefer to think about this, or is it okay if the first problem I discuss and then next few problems you guys will have a better idea? What do people prefer? Okay, I guess just get a understanding of the question for a bit, and then we'll see. Everyone has got the problem? Is there any this thing in the understanding of the problem? People?
No problem.
Okay, great.
No problem in the understanding.
Good. It's an interesting problem, and it's one of my first problems in dynamic programming, if I remember correctly. Okay, so let's get into the idea now. We'll see how each of those 5 steps work out. Step 1 was defining subproblems. So, can anyone tell me what a subproblem would mean in this context of rod cutting?
Like which sum will give the maximum value here?
Partitioning
That
and
would be
taking the maximum value.
Uh, yeah, that's kind of like the next part. The subproblem usually means like because you have rod of length n. What if you have like you define subproblem as rod of length k? Like for a little more general k, like instead of rod, let's say n was 10, you define its subproblems as rod of length 9, rod of length 8, rod of length 7, rod of length 6, and so on. These are all of your subproblems. What you all mentioned is what is the second step. So the first step was defining subproblems, that is the different lengths of the rod. And now the next thing is to guess. So how exactly do we guess?
Maybe we partition it into k parts.
You don't want to partition into k parts because you don't know how many parts you will have to finally partition it into. What
Yeah,
you do know is
but some
how.
of the terms can be 0 too. This is a limitation I'm putting, that they can be 0 too.
Okay, okay, yeah, you can say that in at most k parts or something like that.
Yes,
Uh,
yes.
okay, but again, how is this related to guessing this time? I think what you said last time is more of the guess. I'm not sure if I heard very correctly, but
I said that like we partition it into all the possible values and take the maximum value.
yeah, see that is exactly what is brute force. So if you do that kind of
But
thing,
partitioning will take very much time. Like if we take very large scale, then number of partitions become very large.
yeah. So the number of partitions will probably be exponential, or at least not exponential.
It is greater than exponential.
It's going to be a lot, definitely. I'm not very sure how much it will be, but it's not going to be very efficient. So this is exactly why we need dynamic programming. Usually dynamic programming is a place where the idea is, why is our thing becoming exponential and all? Because we are doing repeated calculations. And the repeated calculation is in the sense that uh, that you have already calculated, let's say you partitioned it into, first time you tried partitioning into 1 and 6. Second time you tried partitioning it into 1, 3, and 3. So you have already seen how it was for this one, but no, that's probably not the best example. Okay, what I should do rather is, let's say n was 7, and first time you tried partitioning it in 4 and 3. Second time you partition into 3 and 1 and 3. So this last 3 you had already seen, but you redid it. And that is the same idea of memoization. This is why it's important to memoize. But okay, coming back to our guess question, the important thing here is to just try each of these 5 steps once. And what we mean to guess is where to cut it for the first time.
Uh,
Do you cut
I
it in
think
the
I
start?
have an idea.
One, two. Okay, sure. Go ahead.
So maybe we try it for 6 and then we try it for a base case and see what is the maximum value of partitioning into how many 2s and 5s and 1s. And then we induct further on.
Uh, yeah, that is basically how it's going to turn out. But yeah, okay. Basically, what you are saying is rod of n will become uh, n minus 1 plus this value of the nth, or n minus 2 plus the value of 2 or something. Okay, we'll see it. You're right. You're on the right track. So guess here basically means to guess where to cut the first time. You could cut either at the first place, or you could cut at the second, or you could cut at the fifth, you could cut at the 10th if you have a value of 10 meter is something. So you, all of these options are there. And what to do when you, oh, by the way, is this even, oh, it's not coming fully. I'm sorry. But okay. So the first answer was that we have sub-problems defined as different lengths of rods, and we guess where to cut the rod for the first time. The next step in our thing was to build a recurrence. Can anyone tell me what a recurrence would be? Here, like a recurrence relation.
It
It
would.
is
Okay, you can speak.
Okay, Arav, go ahead.
it is a series where
Because
every value depends on the previous values.
Yeah, exactly. So it's like I can say rod of length n. Again, I'm writing on my face. Rod of length is either equal to rod of n minus 1 plus value of a 1 meter rod, which is 20k, or it can be equal to rod of n minus 2 plus 120k, or okay, this is not visible, or it can be rod of n minus 5 and whatever 200k, and so on. And basically what you want to do is you want to take the max out of all of these. Is it clear why this makes sense?
then we will have some polynomial time, I guess.
Yeah, especially only if you remember all of these values. So it's like,
That's the thing of memoization you said.
exactly. So basically now if you try to code down this, it's like you'll have a function rod, and you'll input n into it, and what you'll say is if your length is less than 0, if length rather than length, I should say n, like if n is less than 0, then this doesn't make sense. Oh, what have I done? Then there's just 0 value earned. Basically the reason you want to take n less than 0 is, what if you had like original length is 4 and then you were trying to subtract 5 from it. Like here we did n minus 5, but this would also require n minus 5 to be positive. So what you are going to do now is you just say that if it's anything less than 0, then it's 0 value, in fact less equals 0. And if n is greater than 0, then you just say it is max of rod n minus I plus value of a I meter rod for I going from whatever 0 to whatever values of I are there, like different meter rods that are sold in the rocket in the market. And now you just output this max. And here we also remember this value stored in array, and then at the start of the function we will say if uh, in array, let's say ri, so if rn not equal -1, then directly return it, right? Does everyone get the idea? I hope the coding parts are like clear. I've been trying to write it in like basic sense, so that even if you are not very familiar with uh,
But
coding and
actually,
stuff.
how can we train a computer based on the algorithm?
Hmm?
But actually, how can we train the system based on this algorithm?
Why can't we?
How can we?
No, like what do you mean by train the system? You're just
Cal-
telling it to
yes,
keep finding the max of these values,
yes,
and
yes.
like rod n minus I will call rod n
But
minus
we
2
need to
I.
like write
Hmm.
in some particular language that computer understands.
Yeah, definitely. This is just pseudocode. Okay. This is just an algorithm. In algorithms, we usually just think of what the structure of the program is going to be. Then you can code in C++, or you can code in Python, or you can code in Java, or you can code in whatever language you want. That is usually the programmer's job, not our job. As mathematicians, our job is to come up with ideas, to come up with algorithms. And that's the fun part. So yeah, this is basically how you would recurse and memoize. This was step 4. So our 5 steps, we have done quite a few of them. We figured out the subproblems. Then we guessed where we would do the first thing. We built a recurrence. We recursed and memoized. Now final thing is solve original problem. What do we mean by this is basically now you would want that somewhere else in some other function you actually input rod 10 or whatever rod this thing you want, like the like just to tell whatever. This is really an irrelevant step. It's not really that much of a big deal, but the main thing is these first 4 steps. So yeah, this was one cool problem. Did
So here
everyone
we were
understand?
only considering by cutting
Mhm.
into two parts, right?
Okay, so yeah, I should make this more clear. When we say max rod n minus I, what happens is, uh, like this n minus I, basically we are saying max of rod n minus 1 plus value of 1, rod n minus 2. Okay, sorry. Rod n minus 2 plus value of 2 and so on. And what happens is this rod n minus 1 calls the function all over again. So it forgets everything. It comes back over here, but now it's with a different input. And now it's doing the whole thing from the start, and it's going niche and niche, and it's calculating more and more values. And ultimately what will happen is it will figure out all the values and it will come back here, and it'll say, okay, if you did rod n minus 1 in the best way, this would be uska value. You added value 1 to it. Now you went to this, and then you did all of that, except
Oh
this
yeah,
time
I
it'll
get
take
it now.
lesser time. But it'll take lesser time because now you've memoized and you therefore remember everything. But that's the idea, that this is the idea of recurrence, of recursive solutions, where within the function you're calling the function. So it looks like you're doing it only once, but the function keeps going within itself and within itself and within itself. And it's very easy to get stuck in infinite loops actually, if you're not careful that your stuff is always reducing. Like here, if we had a rod n plus 1 by mistake, now this thing would go on forever. And that's not nice at all. So we have to be very careful about these sort of things. But okay, is this clear to everybody? Is there some thing I should explain more carefully? Clear, good. Others also, like other than Aditya, Anurag? Just take, okay, good, it's clear. Um, we'll do few more good problems. I'm confused which one to pick. I have a list of problems here, but okay, I guess we'll do this one. We'll do a problem which is called the longest increasing. Also, is this camera thing a bit inconvenient for someone? Like it's not coming clearly. Is it better if I share screen, or is it okay?
It's all right.
It's all right. Okay, good. So we'll be doing the problem which is called the longest increasing subsequence. Has anyone heard of this? Like, okay, if you haven't, very good. It's good for me if you haven't. If you have, then I should probably do another problem. That's all I meant. Okay, longest increasing subsequence is basically if you have a list of numbers, an array from A0, A1 to AN minus 1, and you want to find out some,
Isn't it Edwards-Zekers theorem?
sorry,
Are we only including the longest increasing subsequence or also decreasing?
increasing. We're not looking into that.
Okay, wait,
I get what you're talking
yes,
about.
we could involve Edwards-Zekers theorem then.
Yeah, but what if you also wanted to print the subsequence itself? Like,
Then it is a headache then.
yeah, it's a headache, definitely. So A0 to AN minus 1, and you basically want to find out, like, let's say n is like 6 or something. So you have A0, A1, A2. In fact, I'll just give you real numbers for the sake of 3, 8, 4, 6, 5, 2, 9. Okay. You want to find out a subsequence from this which is increasing. Subsequence is basically like you can delete whatever things you want. Like, I can delete this. This doesn't look nice. This is looking okay, but like not really. This is not nice. And I'm left with 3, 4, 5, 9, and this is increasing. So it's good. 3, 4, 5, 9 is something we can handle pretty well. So in fact, there was also 3, 4, 6, 9. Now that I think about it, maybe. But either of them work. Basically, the answer here would be like would be 4, because the longest increasing subsequence has length 4. However, what if we wanted to calculate this in general? It's like there are how many subsequences of this? There are around n square subsequences, because not exactly n square, it's like n choose 2, but we can approximate that with n square. And I mean, it's obviously n square minus n by 2, which is a lot lesser, but still. So doing n square operations itself and trying to check each of them is not very bad. I will be honest. It's fine. It's a polynomial time algorithm, and it works. But it doesn't always. It's not always very nice. It's like, what if you had n is equal to 2 into 10 to the 5? Now n square will become like 10 to the 10, and we saw 10 to the 8 operations in a second. So this is like 100 seconds, and usually what you get to do in competitive programming is you get 1 second to solve the problem. So that's not very good. You get 3 seconds sometimes, I don't know. But you basically want a better algorithm. You can always want a better one, even if your brute force is fairly convenient. So yeah, now can anyone first of all um, uh, tell me what seems to be a good sub problems to pick here?
Maybe we divide it into some parts like K, and then we try to find the longest increasing subsequence there, and then we find the longest increasing subsequence in the next one part, so we get a polynomial type, not an exponential one.
No, see, one thing is important. We are getting polynomial even by brute forcing. So that way we are fully okay. But we want an even more efficient algorithm. So we are using dynamic programming. Your idea is perfect. We are going to split this array into parts. And essentially, rather than trying to find out the best in the entire sequence, what we will say is uh, after sorting, maybe we can divide it into sub problems. See, if you sort it, then the entire thing is increasing. What you want is you want to find a subsequence of the original thing.
we
Like,
consider in order to
We can find the minimum value in this sequence, and then we can
okay,
eliminate all the numbers to right that are less than it, because then we know that the subsequence must start at those numbers.
sure, that's a smart idea. So, but what if you have something like 349681? Now, 1 is at the end. What do you
Then we
do?
will delete one and then we will start again with the remaining array.
When do you decide it's better to delete one or to use one?
Um, we cannot use one because it is at the very end.
Okay, what if you had 1, 2, 3? Is it better to use this 1, 2, 3, or is it better to use 3, 4, 6, 8? It's better 3, 4, 6, 8, but you can't tell that very quickly, right?
Yes.
So what you essentially gave was kind of like a greedy algorithm, and these are really useful usually, where you're kind of taking the minimum thing, just hoping it'll work out,
where
and
it
then
can
going on.
explore towards the right.
Oh, right. I keep forgetting this thing. I'll do one thing. I'll just write it again. Okay. So what you gave is a. Oh no! What is this penning? Okay. Uh, yeah, greedy algorithm. So what greedy algorithms do is they kind of make a guess of what seems to be the best thing to do, but there's no guarantee. It's like you thought one will be the best thing to pick first because it's the minimum thing, but there's no guarantee that there is anything after it. There's no guarantee that choosing one at all is okay, and there's no guarantee that not choosing one is also okay. So essentially what dynamic programming is, improvement to greedy algorithms, because we don't guess. Instead, we try out everything in a way that avoids exponential time. It's like dynamic programming is called a careful brute force, which is very interesting. Like a oxymoron, if you know what oxymorons are. Oxymorons are basically when two opposite words are together. Brute force usually means where you're very careless and just try out everything. Careful means where you're like not trying out everything. So that's an interesting thing which is used for dynamic programming. But okay, coming back to the problem. Um, so sorting doesn't work out. Greedy algorithms don't seem to work out. Dynamic programming is giving us an idea of what if we define dpk. Oh, by the way, usually we use arrays called DP, and like just to, DP means dynamic programming here. But anyway, if you define DPK as the length of the longest subsequence ending at AK, increasing, longest increasing subsequence, uh, ending at AK. Does this make sense? It's like basically A0 will become like the longest subsequence that ends at A0. So it'll have to be just A0 itself. So DP of 0 will become 1. A1 will depend on whether A0 was less than A1 or A0. If let's say the array was 3, 4, is it visible? The numbers? Wait, I'll write it.
Yeah, it's
Uh,
visible.
okay, but I'll anyway. 3, 4, 8, 6, 2, 5. So 3 is less than 4. So you can say DP1 is 2, because you can pick two elements in the subsequence ending at 4. You can call DP 2 as 3, because now I can just add this 8. But now when we have reached DP3, oh, this is not visible. So this we cannot say is 4 because now 6 has come in and 3, 4, 8, 6 is not increasing. You'll have to take 3, 4, 6. So this is also 3. Just to give a general idea, this is how the DP should probably work.
So here we can see a recursion happening. Like
What's the
we
recursion
can
happening?
we can consider the first one as 1 plus the max of that BP.
Yes, it's sort of like that. 1 plus max of what exactly though?
Or like we take some dp of k plus dp of n minus k. Then we take such a subsequence of n minus k that its minimal element is greater than the maximum max of the element of the largest subsequence of a dpk.
Yeah, basically, yes, you sort of get the idea. That came over my face. That's scary almost. But okay, but we'll go in steps. It's important to go in steps. First step, we saw what were the subproblems. Subproblems we have got as the longest subsequence ending at k, longest increasing subsequence ending at ak. This is our, okay, that's not coming on the screen. Leave it. So our subproblem we defined. This is done. Now what do we guess? Like to solve dpk, what do we need to guess? I think you all have got the idea. It's just guess is a bit this thing confusing. So the idea is that what you should guess is which was the previous element. Anurag said this also. Before the, because dpk definitely ends on ak, that we are sure of. We just want to guess what was the second last element in the subsequence we are going to guess. So that second last element could have been anything from a0 to ak, right? To ak minus 1 rather. A0 to ak minus 1. And dynamic program tells us when you're unsure about what guess to choose, try all guesses. So what we are going to do here is,
So we can write it as 1 plus max of any one of that DP between them.
exactly, but not anyone. The problem is if ak minus 1 is, let's say, 7 and ak is 5, we cannot choose ak minus 1. So we can only choose this ak minus 1 if ak minus 1 is less than ak. Or in general,
In other
ai
words,
is
the subsequence of dpk minus 1, k minus 1's maximal element is shorter than ak.
yeah, maximum element of that thing will just be the last element, and the last
Yes,
element we know
and
is
that has to be
ai.
shorter than ak.
Yes. So basically, you want ai is less than ak, and obviously i
We
is less than.
basically have to only use k minus 1 guesses, which is not a very large number.
It is actually not very small either, but it's okay. It's nothing. Actually, we haven't been very. Oh, there are not n square possible subsequence. I'm dumb. I'm sorry. So if you had tried to brute force this thing, you would have 2 to the n subsequences. So it is exponential, and therefore you do need a polynomial time solution. So it is actually, I was thinking of continuous subsequences for some reason. I'm sorry. So that means that even though we are going to get a slightly inefficient algorithm here, it is still the best that is possible. Anyway, so basically what you want to build a recurrence now. So what is your recurrence? It says AK, rather DPK is max of um, values going from I equal to 0 to k minus 1 if uh, if this whatever, hmm, Okay, AI is less than AK, then you can say dp of I. So max of these dpi's. I have not read. It's very weird notation. I don't know what I have done with the notation, but rather I think I should have written it like this. Okay, 1 second. But I think people get the point, right? It's like max of I going from 0 to k minus 1, and AI is less than aka of dpi plus 1. Do people get why this works?
Yeah.
Okay, good. So this is our recurrence. Our recurrence is ready. Now we just have to code it. Is it okay if I skip that part for now? I think everyone gets it from a recurrence, how to build back the.
Yes, so the code is not very good.
Yeah, it's the same thing. It's basically you show the base case, you show the this thing, and you memoize. Those are the three important things you should never forget. And after that, you call the original. Oh, by the way, we are not so done, right? We have figured out dp0, dp1, dp2, dpn. But which one here is the longest increasing subsequence? What do you people think? Is dpn the longest increasing subsequence? People?
Maybe no.
Yeah, it can be any of them. Exactly. It is just the max out of all of them. It is like, that the subsequence ends somewhere. It could even end on the first one. It won't end on the first one most probably, but it could. If the entire thing is decreasing, then all of them are one, and then the first one is sort of correct. But it could end anywhere, and you just take the max out of all of dp0 to dpn, and that is your answer. So you take max. Here, this was one extra step. Usually you directly get dp of the biggest value as your answer. This time you had to find the max out of all the dp's to get your answer, but that's fine. Just one extra step. Oh, just to comment on the speed of this, we are figuring out from dp0 to dpn, right? There are n of these, and within each of them there will be n calls to the previous one. Like there'll be k calls, and k we can bound by n. So like it's kind of big O of n square. If you know big O notation, it's basically order of n square kind of. It's like you can say that there are at most some constant times n square steps in this algorithm. So it's polynomial time. Whereas if you had tried to check out every possible thing, you had a subsequence could be any of these, could have like 2 to the n minus 1 possibilities, because you're probably ignoring um, the case where everything is null. But 2 to the n is exponential, so we have avoided exponential time using dynamic programming. So yeah. Uh, Did people understand this? Is there any part that I should repeat? Understood. Good. Which of the previous two problems was better?
So what will be the time complexity for this?
Yeah, I was just talking about that only. Basically, in dynamic programming, time complexity is given by number of cases, number of sub-problems into the time each sub-problem takes. and number of subproblems here is n, because there are dp0 to dpn, and at the end you also have to find max, but that's okay, that just takes n steps. And here time for 1, we had to go through a0 to ak minus 1, and that, and like k you can bound by n, so you can say like n into n, although it's lesser than that, but it's a fair bound. So n square is kind of a bound on the uh, on this dynamic program. So you can say that it's big O of n square. Maybe I should have like made big O. Did I explain big O at the start? I don't think so, right? No. Okay. Basically, big O notation is like if you have 3n square plus 5n plus 6. Like as n becomes larger and larger, these things become irrelevant. This 3 also becomes sort of irrelevant. Only thing that matters is this n square. So we call this 3n square plus 5n plus 6 just O of n square, big O of n square. Especially in like same way, if you had like 2 to the n plus n, this n is like irrelevant in front of this 2 to the n. So we can just call it big O of 2 to the n. So big O basically helps you get like a rough idea of how efficient your algorithm is, based on the fact that it ignores the smaller values and their constants also, and it just gives you like a basic idea on how the program is running.
So we can say the go denotes how fast the function is increasing.
Uh, it not exactly. Like first of all, that would probably be its differentiation. Like that's the rate of change, but
Yeah.
yeah, it's like 3n square plus 5n plus 6. We are basically, what with big O we are just saying is that if you want a very broad idea on how efficient the function is, then it is n square. It's like as n becomes very, very, very large, all of these factors will become irrelevant, and what will matter is your n square. And even this 3 will become very small in front of your n square. So it's not exactly how fast it's changing or like what's the rate of its change, but it sort of gives you an idea of uh, just the general idea of it. I don't know how to explain it better than like that, but anyway, I think people get a general idea. Anyway, big O is something that's important in time complexity. I guess you all can read that up later on. It's very useful and it's there everywhere because it makes it very easy to say how efficient an algorithm is. But yeah, back to one last thing. One last time I'll ask, did people get this problem completely? Is there? Okay, I think I had already asked. It's fine. We'll do one more problem. Or are people bored? Should I give a much harder problem or is the difficulty level okay? What do people want? This level is fine. Yes, that's. I also agree. Anything that gets too hard, it goes over my brains also most of the time. So it's better to pick. Okay. I have two options. Okay, we'll do a problem that's sort of similar to the first problem, but not really. It's like you have to give a shopkeeper 50 rupees or like n rupees in general, bracket rupees n. This is what you need to give a shopkeeper. And you have like unlimited supply of 1 rupee coins, 2 rupee coins, 5 rupee coins, 10 rupee notes, 20 rupee notes, 50 rupee notes. Okay. And you want to find the number of ways. Okay, just to repeat for the people who've just joined, like if you have rupees n with you and you've gone to a shopkeeper and you need to give him 50 rupees or n rupees in general. And you have 1 rupee coins, 2 rupee coins, 5 rupee coins, 10 rupee notes, 20 rupee notes, 50 rupee notes. And what you want to do is figure out the number of different ways in which you can give him all of this money. Like if I can either give him 51 rupee coins, or I can give him 25 2 rupee coins, or I can give him 48 1 rupee coins and 1 2 rupee coin, or I can give him 40 1 rupee coins and then 2 5 rupee coins, something like that. I can do a lot of different things, but I want to find out the number of ways in which I can give him the money.
So can I say something?
Yeah, sure.
So we can divide that n rupees into n 1 rupee coins, and then we can use combinations to check out how much we are dividing into one part.
We can use delimiters easily here. Like
Hmm?
consider 50 objects. The 50 objects can be one rupees coin. So we
Yeah,
have
same thing.
so we can have uh, at most n number of delimiters, and we count from 1 to n. So we get that each time. If you have read Pablo Sobron, you would know.
I get a basic idea of what you're saying, but I
So we are just basically
uh,
dividing into parts where we are combining some parts into variables and just adding them.
I see. I see. Okay. That is definitely a good idea. Um, but just because we are in dynamic programming session mostly, uh, I guess we could work on something of that
The
sort.
number of
Like
ways
it's.
will be come out to be some sum of binomial coefficients.
I guess this might actually have to do with uh, the generating functions.
Yes, but you can first of all consider like some 8 coins, and we have to we can divide them into 1 to 8 parts. We have to make such a choice.
1 to 8 coins.
1 to 10, sorry, 1 to 10. We can either divide it into k parts, one part. I'm sorry, we can at most divide it into 10 parts, or into five, into two, into one.
You can divide it into 50 parts also, right? If you have 50 rupees.
I'm telling for 10 rupees.
Okay, for 10 rupees. Then, but what if you have like 9 parts with 8 1 rupee coins and then 1 2 rupee coins?
Yeah, I'm considering the same. We can use the limiters very easily.
I see. Okay. Uh, so this is a problem that has got killed, but just for the sake of a dynamic programming type approach, because that's very nice. It's actually a very easy problem. I thought I will start with this problem, but then I thought I'll start with the cooler problem. So yeah, this is just a simple Fibonacci, like kind of like a recurrence. Like this is like f of n will be equal to f of n minus 1 plus f of n minus 2 plus f of n minus 5. A lot of ways to go about this, definitely. But plus so on, whatever. Right? I'm not even bothering to write this on this. It turned out to be too easy problem. Uh, I wasn't expecting it to be this easy. But anyway, f of n minus 10 and so on. And now you just build the same way. We didn't even have to do defining subproblems, guessing anything. We're not guessing anything. What are we doing? Uh, there will be multiple counting. Like, that's the idea of memoization. There'll never be multiple counting if you have memoization. Because you're right. I think what you're saying is that you'll end up, when you do fn minus 1, you'll end up doing fn minus 2 again. But by that time, you have already calculated it, and therefore you directly return it. So you don't actually waste any time recalculating stuff when you have dynamic programming. Is that okay, Arif?
So some problems can be killed directly using matching.
Lot of computer science problems can be killed with. Like I've seen one problem in some US. Hmm? Sorry.
I'm saying almost every problem can be done using mathematics.
Yeah, like lot of uh 5 rupees. Okay, let's just read this quickly first. 5 rupees and 10 rupees, 10 rupees, 5 rupees. Oh, yeah, so the thing is, when we say this question, we are counting them as different things. We're counting 1 rupee and then 2 rupee, as I should have probably mentioned this, but 1 rupee and 2 rupee different from 2 rupee and 1 rupee. And so it's all right to spend an extra second calculating that, because that does count in our final thing. If it doesn't count, it's a little harder to solve the problem. Then you will have to stick to mathematical approaches. That is very nice actually, but I don't think dynamic programming will work if you have to, uh, if you don't care about the order. But okay, I was saying there was this problem in USACO, I think USA's Computing Olympiad, which was like, uh, I don't know, it like, no, it wasn't in USACO. I'm sorry, it was in some Google competition, and if people have heard of that ants problem, it's a very common one in a lot of places where ants bump into each other and they reverse directions. Has anyone heard of that here? Yes, I know it. Okay. So if you know it, then you know the key idea is to forget that they change directions and stuff like that. Like there were a lot of like that problem just got trivialized by the fact that like you can forget that they reverse direction. So it didn't get trivialized actually. It was still very hard, but I actually didn't get it even after that. But it got a lot more easy to solve with that. But anyway.
Last problem of
But
INOI this year was also DP, right?
Uh, I don't even remember this year's INOI. It was like so much harder than the previous INOIs. It was, but still, what was the third problem? The third problem was some graph. I don't remember. Okay, we'll do it at some point at the end. Maybe we'll discuss it. I have one more cool problem, and this time it'll be different from the others. Oh, it was copied? Wow, I did not know that. Interesting. So this will be quite different from the others. So this should be interesting. Let's say we have a grid of m by n. And some cells are blocked. And you start over here and you have to finish over here. And in any step, you can go either up or right. So one way would be to go like this, then like this, and like this, then like this, then like this, then like this, and like this, like that. Or you could go like this at the end or something. I hope people have got like a general idea. So basically the question that is being asked is you want to find the total number of ways of reaching this final spot.
can I tell?
Sure.
We can easily include principle of inclusion and exclusion here.
Hmm.
So
How
like
exactly?
we have the number of octagonal paths as m plus 1 choose m, and then we have some point
M
AIAJ.
plus 1 choose M plus n choose M is usually the thing, right? If there is
They
no
both
block
are the
cell.
same. M plus 1 choose m is equal to m plus 1 choose n.
M plus 1, no, it's usually M plus n choose.
I'm saying n.
Okay, yeah.
Yeah. Then we can like there is some point I into k. So we can count the number of paths from origin to reach that point, from that point to reach the final point, or some. And in the third exclusion, we can count from reaching this point to reaching another point and then reaching to the final point. This is how we
No, but
can do it.
how are you considering the fact that these cells are blocked?
You told it that they are blocked.
Oh, I meant that you cannot go through these cells. Like you cannot go like this.
So
This is
that's
not
why I'm
allowed.
excluding the paths. That's why I'm
Ah,
Okay, so
excluding the paths containing
yeah, it's
these
okay.
cells.
Just count the number of ways in which we can go through a single path to from this point to that point, and then the
up
number
and
of
right.
ways for which, yeah, that up and count the ups and count the rights, and then use a relation with repetition steps. It's being in a mathematical
then-
way, and then subtract the of ways in which we can go to these blocked cells.
So you're saying you're subtracting number of ways where you have gone through at least one block thing.
We can use
Yeah.
principle of inclusion and exclusion here. Like if we have one, we consider first that we go through one block cell, but in that part, the second block cell can also occur. So in the second part, we
So-
add that part that two simultaneously occur on a path, and then we keep excluding and including it depending on the number
Yeah,
of block cells.
definitely works. But how fast would this be? Because you will have to uh, okay, first of all, how are you going to figure out number of ways through two different blocked cells? Let's say, like for this inclusion exclusion, you'll have to say, let's say I went through this and this. What are like, how would you calculate the number of ways which
I firstly
you
calculate the
can?
number of ways to reach the first
Oh,
block
from
cell,
1 to 1
and
and
then to
okay,
that, and then to the
okay.
final point.
That works, but it seems a bit
Yeah,
slow.
but
Like
it's simply just yeah, like I mean, count ways in
it's
which you can go from
exponential
this
in the
initial point to the
it's exponential in the number of these blocked cells, right? Like if you have 5 blocked cells, then you're considering like in each combination of them being chosen or not being chosen, like these 3 chosen, only 1 chosen, everything. So it's 2 to the 5. And if everything was blocked and your grid was rather large, then it can get really bad, right?
yeah. So what if you count the number of ways from the initial point, say I, and then you go to J.
Hmm. What
The
is
number
J?
of ways. I mean, just 2 points. Just say the initial point is
Like the
some name
final point
or
or
something.
any point?
Yeah, the final J.
Okay.
Okay,
Then
it's I and J. Then you count the number of ups and rights and use repetition to find out the total number of paths to go from this I to J using ups and rights.
but there could be blocked cells in between, right?
Yeah, so that means we have to subtract it.
So we exclude
Yeah,
them
so
in
we
the next part.
exclude them. So we exclude the what? Exclude
Okay.
the number of ways in which we can go from those blocks, go to those block cells from the initial.
Yeah,
point.
that's what Anurag was saying too. But the thing I'm trying to say is that in each of those, you have now in inclusion exclusion, you have to consider each case. Ki one thing was blocked and you visited, then 2 things were blocked and you visited both, and 3 were blocked and you visited all 3, something like that. So it
But we then need to count the number of block cells that lie on the optimal path. Then it becomes like some sorting. Like it is not necessary that all block cells lie on the optimal path.
no,
Only some of them can lie.
yeah, in one particular only some will lie, but it could be that all of them lie, it could be that none of them lie, but the idea is that
Then we can use the bounding, I guess. Like if AJ and AK are such points, then XJ is smaller than equal to XK, and YJ is smaller than equal to YK. We get such type of bounding which helps in sorting out.
okay, so sorting is helping, but honestly, like
It won't
it
really
doesn't
get
feel like
that
it's
big, I
worth it.
guess.
Yeah, it won't get
mean,
very
I
big
also
here
don't
because
think
there are only 5 blocked cells. If your entire thing was blocked, then imagine, like, then you will have to consider two are blocked, 32 are blocked, like that. Then it's just getting too much, right?
I'm telling for the 32 block parts only. Then we easily get a bound and we can try to reduce the number, which always helps.
Yeah, I still don't feel convinced it's worth it, like so much effort for this problem, because it has a really easy dynamic programming solution, to be honest.
Yes, it is getting a more complicated. Like in every step, we are adding something.
Exactly. It's like so much effort for this seems a bit unnecessary to me. It might work out. I'm not very sure, but really doesn't feel worth it, because there is so much of this casework where 3 events are there. How are you going to code such a thing? Like, you'll have to do a
So we
lot of
need to
work
add
for it.
many limitations. We have
Yeah,
very many.
it's lots of I don't know, but it definitely does work. I'm not arguing that. I'm just arguing its efficiency. But okay, to think of a dynamic solution to this, we have to follow our steps. uh, what is the first step? Sub problems. Can someone tell me what a nice sub problem would be here?
Or maybe to reach another unblocked cell, which lies on our program.
Yeah, sure. So DP, instead of 1 dimension, what if we extend our thing to 2 dimensions?
Consider I and J.
DPIJ.
Yeah.
Yeah, this refers to the number of ways of reaching I comma j. Like I comma j is just the, like, you can take this as, I don't know, 0, 1, 2, 3 till m minus 1, and 0, 1, 2, 3 till n minus 1, whatever. I mean, you can usually take from the top, but that's all fine. So we got, oh, I'm not, sorry. First, we got the subproblem as dpij. This is nice. Now, what do we guess? What seems like a nice guess to make about dpij?
It will be the initial point and they will be the point where we want to reach.
No, we already have dpij as, like, from the initial point to this point. What we want to do is we want to make a guess that kind of relates dpij to other dp values.
Then if we reach that IJ, we need to reach the final point, I guess. Then we have some recurrence.
Yes, it's basically that you kind of guess what is your last move. Is it, have you come here from the right or have you come from upper? So if you have come from the right, then this is like dpi minus 1j. Like whatever the left wale value ka tha, and now you've come here. Or you could have come from niche, in which case it is dpi j minus 1. So it's either you've come from the right or you've come from down, and those two,
It's
and
kind of a Fibonacci sequence.
yeah, but in 2 dimensions. It's like 2
Yes.
dimensions. So this guy will tell you from here or from here. It's a Fibonacci in 2 dimensions, you can say. It's interesting to think of it like that. But the important thing to note here is this is only if it is unblocked. If dpi j happen to be blocked, then directly 0. So what this will also do is, if you started off with uh, this wala guy and you saw left mein, it'll be 0 ways because you cannot come to the place from the left because that place is just blocked. So you can only come from niche, and in that case it'll be only dpij minus 1. So yeah, we have basically got a recurrence. Recurrence is dpij is equal to 0 if blocked, and if it's not blocked, then dpij is equal to sum of dpi j minus 1 plus dpi minus 1, sorry, j. Yeah, this is like the Fibonacci in some ways, we could say, maybe. And yeah, this and now you
And then we
call a
memorize
function.
every value.
Exactly, that's very important because here there'll be so many things that are coming again and again, so you have to memorize. And we're done. Yay. So essentially, there are a lot of problems that require you to use DP in 2 dimensions. Sometimes in more, usually you don't see 3 dimensions because then it becomes very, very big, because like 10 to the 3, agar ek mein hua, then 10 to the 3 into 10 to the 3 into 10 to the 3, it's too big. So like you don't want to waste that much space of your computer also. Like that, you need to have a balance, right? You want to memorize to remember stuff, but you also don't want to remember so much stuff that your computer gets overloaded. So basically, usually we stick to 1 or 2 dimensions, and it depends on the problem completely. Sometimes in like problems which are very similar to the one we did earlier with these coins and all, they can also require 2 dimensions. It's like, what if you had to use dp of I and s here, where s is the remaining weight to consider. It's like, I don't know. No, I is not really a thing here, so it's not a greatest example. But sometimes you will require to remember 2 things about a certain process. So there also you require 2 dimensions. So yeah, I guess it's 8:30. I think I have uh, exhausted my problems also. I hope all of you enjoyed to some extent at least. It was my first class, so if any of you have any feedback or something to give, I would love to hear.
I'll end the recording.
Yeah, okay, sure.